Hi everyone, let's start Module 3, Sound Waves. In 3.1, I just want to go over a brief introduction to sound waves. And the first thing to review is that sound waves are longitudinal waves. Remember that longitudinal waves are waves where the displacement of particles in the medium is parallel to the direction of propagation of the waves. Sound waves are mechanical waves, so they do require a medium to propagate, and they can travel through solids, liquids, or gases. Particles in the medium will oscillate to produce regions of high and low density and pressure. So these regions of high density and pressure are called compressions, and then regions of low density and pressure are called expansions or rarefactions. And by oscillating through these regions of compression and expansion, the wave will transfer energy throughout the medium. Often we're concerned with sound waves in air. For sound waves in air, the speed of sound increases with temperature according to this relationship. V, the speed of sound in meters per second, equals 331 meters per second times the square root of T, temperature in degrees Celsius, over 273 degrees Celsius plus 1. And at room temperature, if you were to plug in about 20 degrees here, you'll get a speed of 343 meters per second, just as an example. And you can use this value if the question just says at room temperature. Otherwise, we can plug in the temperature and calculate the sound speed. So also, these are waves. The wave equation we've seen before for the speed of the wave still applies here. V equals lambda f, where lambda is the wavelength and f is the frequency. If we consider a spherical sound source, that wave would propagate in all directions unless blocked. For now, we're going to consider one-dimensional waves, such as a wave in a sound tube or in an air column, that only do move in one direction, one dimension. And because the sound source can be something that's a simple harmonic oscillator creating these vibrations, then the density will also oscillate as a sinusoidal function. So we could write density or pressure here, and they would both oscillate with a sinusoidal shape. Example 1, a tuning fork is struck outdoors on a day when the air temperature is 8.5 degrees Celsius. If the fork has a frequency of 512 Hertz, what is the wavelength of the sound wave? Okay, so first we want to use the formula to find the speed of sound at 8.5 degrees Celsius. So just plugging in 8.5 degrees Celsius here gives me 336 meters per second. And then with that, we can find the wavelength, which is V over F from the wave speed equation. So 336 meters per second over 512 Hertz, which is 0.656 meters for the wavelength. Example 2, you stand on a rock ledge 412 meters above a lake on a summer evening and drop a rock. How long after you drop the rock do you hear it splash? Okay, and let's assume the speed of sound is 343 meters per second. So it looks something like this. You're standing on the top of the cliff. I've moved it over, but at this height, and you drop the rock, and then you don't hear the sound until the sound wave from the splash travels up that distance and reaches your ear. So we have two portions of the problem where we'll need to find time. So we need the time it takes the rock to fall, and then we'll have to add on the time it takes the sound to travel back up to the height of the cliff where your ear is, approximately. Okay, so this is a free fall problem to start, so a bit of 1D kinematics review. We have Vyi is 0, delta y is negative 412 meters since the rock moves down 412 meters, and I'm going to use down as negative. And then our acceleration is the free fall acceleration, negative 9.8 meters per second squared. So we need to choose a kinematics equation that works here to find time. So it will be delta y equals Vyit plus 1/2 AYT squared. And if you use different notation, that's not a problem. And then that term is 0 since it starts from 0. Okay. And then we can solve for the time. So the time it takes the rock to fall is 2 delta y over a, and the root of that. So that is the root of 2 times negative 412 meters over negative 9.8 meters per second squared, which is 9.17 seconds. Okay, so that's the first part, T1. Let's call that T1. Then we need the time for the sound. So the sound is moving at a constant speed in air of 343 meters per second, acceleration 0. Delta y is positive because it moves up 412 meters. And we can essentially use this formula again, but this time it's this term that's 0. That's 0 now if we're talking about the sound. So we have delta y equals Vyi, which is the same since speed is constant, so Vyi, Vy, Vyf, all the same. T2, so T2 equals delta y over Vy, which is 412 meters over 343 meters per second. So 1.2 seconds. Okay, so the total time it takes to hear the splash will be 9.17 plus 1.2 seconds. So 10.37 seconds. And that's fairly significant, though this is a high cliff. The displacement of a longitudinal wave is the same as we've seen before for other sinusoidal waves. Here, y at x and t can mean the displacement of the particle from equilibrium in that one dimension that we're looking at. It doesn't have to be vertical. In the next section, we'll look at how this applies to standing sound waves.